All right, one thing we're going to examine is why not use 100% confidence, okay? We talked about using 95% confidence, 90% confidence. I gave you another one, 99% confidence. But why don't we use 100% confidence, okay? And to understand that, let's see why. Let's go ahead. We're going to examine our error formula, okay? So this is the population standard deviation. They tell us that in the problem. They tell us the sample size. Now, notice as the sample size gets bigger and bigger and bigger, this denominator keeps getting larger and larger and larger. So I'm dividing by a bigger number. This overall term is smaller and smaller and smaller. So as our n gets larger the sample size we get, the smaller our error value is. Which makes sense because the larger of a sample you take, the closer the average of whatever you're looking at should be near your population average, okay? If I asked everybody at CLC what their age is and computed the average, except for one single person, so I don't have the entire population of CLC, I have a population minus 1. So in that sample, if I were to find the average, it should be very close to the actual population average. Okay, so as n gets larger, the error gets smaller. But now this value, let's examine this value. Let's see how we got this number. Z of alpha over 2 is equal to inverse norm of alpha over 2, comma 0, comma 1. Now, what did that do for us? Okay. When we specify a confidence level, let's just say we're at 90%. So then our alpha would be 0.01, 0.1. So that means our alpha over 2 is equal to 0.05. When we get our point estimate, we want to be sure that 90% of the data lies within that interval right there, okay? So, how inverse norm works, it always finds the area to the left, okay? So in this area is my confidence level, or 0.9. Over here in this tail and in this tail, if the area underneath the total curve is equal to 1, and this constitutes 90% or 0.9 of that total 1 of the area, this side plus this side should be the other 5%. And that's what we're finding when we find the alpha value. We are finding the area that's in these tails. But now since there are two tails, that's why we divide alpha over by 2. So over here's alpha over 2, in this case 0.05. Over here's alpha over 2, which is equal to 0.05. So now, here's 0. When we go out to this number, I'm making a number up right now, okay? Let's say we're doing some problem and this value right here, when we type it into inverse norm, is 1.2. That means this one would be negative 1.2. Oh, I guess since we're, whatever. Just made numbers up for right now. Illustrate the point. Now, if you notice, if I make my confidence interval larger, let's say I make it 95% now, so then my alpha is 0.05, so alpha over 2 is 0.01, right? 0.01, so that means my tails are located further away because now I gotta fill in more area to fill up that 95%, okay? Since my tails are further away, when I calculate this inverse norm value, I'm going to be at a further number. Let's say 2.6. Over here it'd be negative 2.6. I wrote 2.2. So as our confidence level goes up, our alpha value gets smaller. And because our alpha value gets smaller, our z values get larger because they get further and further away from 0. Okay? So as you could think, if this gets to 99, this is going to be a smaller number. I'm going to be even further out over here. So this number is going to be really large. So I'm multiplying a really large number by another number. This is going to be large. So as I get closer and closer to 100% confidence, this number gets smaller and goes to 0. Therefore, these numbers, these z values, gets further and further down the number line, and they get bigger and bigger, and they approach infinity as we get our confidence level closer and closer to 100. But then that means our error grows bigger and bigger, okay? So the higher the confidence level, the larger the error. The smaller the confidence level, the smaller the error. But then using a small confidence level makes us more uncertain about our results, because if we were to use a 75% confidence interval, well, now we're only 75% sure that our interval contains the true population parameter, whereas using a 95% confidence interval, we're 95% sure. Okay? So, that's why we don't use 100%. It's a good question if you had that. Why don't we use 100%? Now, I should have left the formula up here. E is equal to z of alpha over 2 sigma divided by square root of n. Sometimes you want to work backwards. Sometimes you know how close to your answer you want to be, so you know your margin of error. You are predetermining what your margin of error should be. This you get from the confidence level. Now, we haven't really talked about confidence levels and where they come from. That's something normally set by the researcher, the one doing the work, okay? In different areas of sciences, they use different confidence levels. Like social sciences use like a 90% confidence level. I think in pharmaceutical companies, they use a 99, something like that. We'll come more across that in Chapter 9. But this relies on our confidence level. We normally know this. This is given to us in the problem, or we usually can find this. What we want to know is how big of a sample do we need to ensure our chosen accuracy. We're choosing this. How big of a sample do we need? In the previous problems, we were told how big the sample was. We were told this. We could find this. Told the sample size, found the error. Now we're being told the error, we need to find the sample size. So if you were to do a little bit of algebra and divide by z of alpha over 2 on both sides, you get e divided by z of alpha over 2 is equal to sigma divided by square root of n. Now if you were to cross multiply, you get square root of ne is equal to z of alpha over 2 times sigma. Divide both sides by e. Square root of n is equal to z of alpha over 2 sigma divided by e. And then you're just going to square both sides. N is equal to z of alpha over 2 times sigma divided by your error, all of it squared. Just some algebra to get this result. Again, if you have my lecture notes, this formula is in them, so you can just reference there. It's also in the book. But let's go ahead and do an example on how to find sample size. Let me write the formula up here. N is equal to Z of alpha over 2 times sigma divided by the error, all of it being squared. So the problem on my notes says the population standard deviation for the age of football college students is 15 years. So they told us the population standard deviation is 15 years. If we want to be 95% confident, so they tell us the confidence level is 95%. Okay, so it says that the sample mean age is within 2 years. So our sample mean age must be within 2 years. That's our error. E is equal to 2. So we're predetermining what our error should be. And now it says how many randomly selected football college students must we survey to ensure with the standard deviation of this, confidence interval of this, and our predetermined error. So it's really much just plug everything in. The only thing you need to calculate is the Z of alpha over 2. So alpha over 2, I'm just going to give you the result real quick. 1 minus alpha is 0.05, or sorry, 1 minus 0.95 is 0.05. 0.05 divided by 2 is 0.025. So, Z of 0.025 is equal to inverse norm 0.025, comma 0, comma 1. We get out our calculator, use inverse norm 0.025, comma 0, comma 1, paste, and we get negative 1.959. Now, when we do it here, it doesn't matter whether you make it positive or negative in this case. You only want to make it positive when you're actually finding the intervals. Here, you could leave it negative because if you plug a negative number into here, you're squaring it. It's going to turn out to be positive anyways. Now that we have every number we need, we can go ahead and calculate our sample size. So Z of alpha over 2, we just found it right here. So 1.959. I already made it positive. There's no reason to write the negative. Times 15 divided by 2. I'm going to square everything. So just plugging everything in the formula. Now, we don't have a calculator function that'll do that this for you. This one you actually have to do by hand. So I got 14.6925 before I squared it. So 14.6925. That's just computing the inside. And now I'm going to square it. And I get 215.869. Okay, so that is the answer. However, that's not the full correct answer. We're surveying college students, and it's supposed to be a whole number. Can we survey football college students, 0.86 of a person? We cannot. So do we round up or do we round down? Give you guys a second to think about it. You are always going to round up, okay? The reason being is because if we go back to our original error formula, it's Z of alpha over 2 times sigma divided by n. Let me clear up some space here. See, we don't need this. We got our answer right there. Here, I'll write it bigger. Error is equal to Z of alpha over 2 sigma divided by square root of n. When we're calculating our error, we want to make sure it is exactly 2 or smaller, okay? We want to be within 2. We don't want to be larger than 2 because that's what the problem was asking. To get exactly 2, this calculation that we did here, would give us an error of exactly 2. If we were to plug this number into right here, you'd find out. You would get exactly 2. Okay? Now, if we were to round down, the denominator would be a smaller number. Since the denominator is a smaller number, the overall number is going to be a larger number. You could think about it like this. If I take 10 and divide it by 5, it gives me 2. But then I take 10 and divide it by a smaller number. Let me divide it by 2. I'm going to get 5. Okay? So the overall number got bigger. That means our error is going to be bigger than 2. So if we round up, the denominator is now smaller. Or sorry, the denominator is now larger. My fault. I meant to say larger. The denominator is larger. Since the denominator is larger, the overall number should be smaller. Okay? So we're going to always round up. So the answer here is we need to survey 216 college, oh, I kept saying football. It was Foothill. Okay, Foothill College students. Okay? And that concludes 8.2. When we go on to 8.3, it's going to be very, very similar to 8.2 that we just did. The formulas are going to look almost identical, but we are going to be using a t-distribution. And I'll show you how to compute those in the next video.